आपको चाहिए ना? हाँ जी. Yes, good afternoon. From last 3 days, we have learnt about the design of hydraulic models and mathematical models. First, I explained about the how to design a physical modeling. In that, I explained about the geometrical, how we decide geometrical scale and distorted scale, which geometric scale is used for which type of structures like spillway modeling and reservoir sedimentation, flushing type of hydraulic structures we are using. Geometrical is similar model. And while coming to the large rivers, we are doing distortion, horizontal and vertical. And this is also explained in my earlier lecture. Now I will explain about the hydraulic structures and construction materials used in river engineering studies. Before going to the model studies, either physical or mathematical, the modelers should know the how to read the the project plan and elevation of the project hydraulic structures given by the project authority. So now I will explain how we should read the diagram, what are the components of the hydraulic structure, and how we replace in the physical or mathematical model, and how we will run the physical and mathematical model, and what are the design aspects we are doing in physical and mathematical model studies in our CWPRS. So construction of hydraulic structures. Hydraulic structures construct across the river for various purposes like, as all of you know, hydraulic structures we are constructing across the river for various purposes like to store water and divert for irrigation, municipal use, industrial use, power generation, for transportation, for navigation, for flood control. And types of hydraulic structures are barrages, bridges, intake structures, embankments, spurs, and guide bunds. In barrages, this is generally used for store the water and divert the water from the river from left bank and right bank. In this barrage, there are many components are there like spillways, undersluices, divide wall, and stilling basin, energy dissipators. Like there are so many components in this barrage. If you want to model a barrage, mathematical modeling or physical modeling, you should know about all these parameters. Under sluices are also there, where you have to place the under sluices, where we should put the divide wall, where what is the hydrogulator, and what is the use of all these parameters you should know before going to the modeling. While coming to the bridges we are using for transportation from one bank to the other bank. So we are only mostly constructing bridges for transportation purpose. In this only the it consists of number of piers and approach road and slab like this. Suppose this is a river. Want to construct a bridge. These are the bridge piers. This is the plan I am showing here, and these are the approach back. Both sides. Only waterway we have given here for flowing water from upstream to downstream. Suppose the river width is 3 kilometers here, and if you calculate the waterway, places waterway, it will come around suppose 575. only we are giving waterway of 575. Rest of the whole width we are closing. Water only coming from this portion only. So for this, we are designing guide bunds on the left bank and right bank, so that the discharge which is coming from the upstream, suppose Q we are taking 25 years, 50 years, 100 years. Maximum discharges we are studying on the model as mathematical or physical model that should pass safely from the upstream and downstream. So these guide bunds are guiding the flow from upstream, and the whole discharge will passing through this only this waterway only. So in physical model, we are studying the total flow conditions after placing this bridge or barrage in the model, and we will by our naked eye will see how the flow velocities are hitting these banks and these guide bunds. This is the shank portion. These are the curved portions, and these are the piers. Suppose any bridge is on the downstream or upstream, how it is affected by this new bridge. You construct a new bridge on the upstream or downstream, the existing bridge, the effect of the new bridge on the existing bridge also we are studying. Tomorrow we'll tell you, and we'll go for hands-on training. Before constructing a structure, first we have studied without models, without a structure. Just existing condition we are studying. We are releasing water. To know the location of the hydraulic structure. Okay. So first of all, you have to know the flow conditions here, and you have to calculate all the hydraulic parameters here. After that, you place a small replica of small model of the hydraulic structure. Again, you conduct the model studies. In between this, you have to go for calibration and validation. Yesterday I told. For that, the maximum, the discharge which is maximum observed on this river or channel, the project authority should give the, suppose the discharge is 2400 meter cube per second, the corresponding water level is suppose 203.5 meters. Like that, you have to give for verification. In 3 points locations, suppose this is the river on the upstream and downstream and at middle. At 3 points, you have to check the water level for that particular discharge. This will give you the model calibration. For verification, you have to go for other discharge you have to run, and the water level are matching or not, you have to do for calibration, verification like this. So this is the barrage, bridge, and intake structures are structures. The some like NTPC, NHPC, they are drawing water from the nearby river for their cooling purpose and other purposes. So they have to extract water from the river, and these intake structures are also we are designing in CWPRS. So this is also we'll study in CWPRS. And embankments. What are the embankments? Suppose river is flowing like this. Some Q 1400. So the banks which are existing banks of these two. So the river is flowing like this. So existing banks are overtopping at some locations like in this reach 500 meters, somewhere here 200 meters, somewhere here 100 meters. For existing conditions. First of all, we are doing mathematical model studies for Q for 2400. And after that, how flow water levels we are finding out on if any from 0 to 10 kilometers on left bank and right bank, the embankment, if anywhere we have, particularly we have seen any breaching, the overflow at embankment we are studying in first existing condition. After that, if you find any overflow, then we have to measure the water level there, and we have to add the freeboard, and we have to decide the top level of the embankment. That is levees, we call levees, and we should design the levee structure. This is the embankments we are studying in CWPRS. Next, spurs. Spurs are the structures suppose water is flowing in a curvature. So in concave bank, this is convex bank, flow is coming like this. Scour is taking place in this convex bank, and deposition is on the opposite bank. This is convex bank. So if you put a structure like this, a spur, so that it will divert the water from the bank, and it will save the bank. These are the spur we are using in river to save the protect the banks from erosion. And the guide bunds, just now I explained about the guide bunds. So these are the hydraulic structures we are using in river modeling. So data required for model studies are index plan, plan of the project, and contour plan for the proposed site, longitudinal section. As in mathematical model, you have seen the longitudinal water surface profile. Like that, longitudinal section and cross sections also important in physical modeling and mathematical modeling. Soil samples for obtaining properties of soil, uh, properties of soil nearby that hydraulic structures. We need the F value, silt factor value, and pi value for design these structures. Borehole data. So where is the hard rock is existing nearby that structure? We should know about the hard strata of the nearby that hydraulic structure, and daily rainfall data for knowing the 25 years, 50 years, and 100 years flood. Gauge discharge relation, just now explained about the validation calibration. For that, gauge discharge relation of the particular for particular discharge in this study reach is also very much important for model studies. Sediment data is also very much important in modeling of rivers. Selection of site. As we are civil engineers, while we are doing in our bachelor degree or mathematical master degree, everyone should know the river reach should be fairly straight and stable reach we have to select for the construction of hydraulic structure. This is the first thing. If you want to go to construct a hydraulic structure in this curved portion, what will happen? The purpose of the barrage or bridge, 100% you can't get the purpose, the results from that hydraulic structure. How I will explain you now. Suppose you are constructing a hydraulic. If you select the site at curved portion, if you construct a bridge here, then what will happen? Flow will be like this. So total flow is flowing from this. If you have given 10 bays for water flow, only 5 bays for actively flowing water, and in other 5 bays there will be a siltation on the upstream, so that this will be choke up. Only cover will be very high at this position and siltation is very high. If you are constructing a barrage, so barrage is for diversion of water. So in every barrage, there are head regulators are also there on the upstream of the barrage. So this is left bank head regulator, and this is the right bank head regulator. Suppose two states are there like Bihar and Uttar Pradesh, and both the banks. Suppose Bihar is in this place and Uttar Pradesh in this bank. So they want Q equally, 50 here, 50 here. What will happen? You select this concave, this curvature portion, location as curved portion. So again, water will be flowing in this way. Only 5 ways are actively flowing, and these will be choke up, and this head regulator is not working properly. And Q50 you are not getting the entire 365 days, and they will suffer. And these people will get every time this discharge. Between there will be a quarrel between UP and Bihar. Like this type of problem, they are up to Supreme Court also they are looking for this type of problems. So we have to before construction of barrage, we have to study the flow conditions nearby this barrage so that the flow is always going from this barrage or bridge should be non-slitting, non-covering velocity you have to reproduce in this place so that always all the base of the barrage or bridge flow without any siltation or covering. And the next one is natural banks should be fairly high and well defined. Minimum width between the Khadir banks is predefined and preferred. Nodal point means if you go the satellite imageries of this particular location in NRSC site, the water should be available at this point. Suppose you are taking the intake structure. What is the purpose of intake structure? Here NTPC is there. They want water from this Ganga river. So they want to take water from the Ganga river for their cooling purpose or something. So they want to construct a intake structure here. So for that, the first study you have to do for there is a you have to find out the nodal point. Nodal point means the water should be available at very lean period also. In the past 20 years, water should be there. That type of location we have to select for extract the water for intake structure. If you in NTPC bar, what will happen? This is in Bihar. So we have decided one location. While construction, they put the street files along this uh, location so that river goes from 1 to 1.5 kilometer from this portion. There is a huge sand bar nearby this location. Again, they approached us and we went site visit and we told if you remove this street files again, river will come to this place because that is a nodal point. Always river will automatically come to that point. So you should know the nodal point in this intake structure so that water will be, they can extract water in lean period also. Clay strata should be avoided. You know, all of you know. Design flood discharge. Yesterday in our one lecture, Punjir sir explained about the 25, 50, 100 years discharge, how we can design from the CWC unit hydrograph method. And by using this design of waterway, guide bunds, approach bunds, river training measures and protection works, we are carrying out. What we are doing, suppose for design of flood protection works, we have to take 25 years design discharge. Now it will be revised into 50 years. At the location, it will depends upon location also. This 25 years we will be taking agricultural lands like forest area like that. 50 years in nearby agricultural lands and 100 years for cities like Surat, Delhi. Now we are proposing 100 years flat for flood protection works. And for design of bridges, barrages, that, that is Q is equal to 20 years discharge. Now it will be divided into 100 years period discharge. So like that, which discharge you have to choose for which type of hydraulic structures, study of hydraulic structures. So normally we'll uh, we have 25 years, 50 years, 75 years, 100 years discharges. We can extract from this CWC method, unit hydrograph method. And gauge discharge relation. Just now explained, gauge discharge curve are useful in calibration studies. Observe data using one and corresponding water levels at minimum 3 locations at the starting of the model, in between the model, at the end of the model. So at these 3 places we should calibrate the model. Waterway. How waterway is important I just now explained. Waterway includes the width of spillway and undersluice portion between the abutments including pier thickness. And we can uh, calculate the waterway by using this Lacy's formula. P is equal to 4.83 under root Q, and the discharge is calculated by yesterday that Mr. Kunjir sir was explained about this. Q is equal to CL H power 3 by 2. And design of a barrage. The design of barrage is includes of many structures. So first of all we have to decide the waterway, and waterway should be the actual waterway to the Lacy's waterway. This is looseness factor should be 1.2 to 1.1 to 1.2 for silt factor less than 1, and if silt factor is less than greater than 1, it should be 1 to 1.5. Shave factor, the spillway crest I am telling, shave factor of spillway, the upstream slope should be 2 is to 1 and downstream slope should be 3 is to 1 to for making the rapidly varying flow. Otherwise sudden drop will be there. So to reduce that flow, 2 is to 1 on upstream and 3 is to 1 on downstream shape of crest we have to consider. And this is the diagram of the barrage. Here you can see flow is like this in this direction, and this is the total waterway of. You have to read the first the diagram of this barrage. They will provide the plan and sectional elevation and all other drawings they have provided to us. Before that, you should know the what is the actual waterway they have provided. From this to this is W, and these are the PS. You see, these are the PS, and this is the spillway, and this is the undersluice portion. This is the divide wall. How many of you know what is the divide wall? What is divide wall? It will divide the undersluice portion and spillway portion. If you don't know that, then how you design the barrage? This is the undersluice portion. There are two undersluices they have given. The undersluice, the crest level of these undersluices are below 1 to 1.5 meter below the spillway crest. Suppose spillway crest is like this. 105, then it should be 105. So what is the use of this undersluice? These undersluice are using for flushing the silt, and lean period water is flowing from this barrel at drawdown level also. So this is the undersluices, and these are the spillways, and this is the head regulator, and these are the water wafer. This is the water wafer head regulator. This is the left head regulator and this is the right head regulator. So water will stop here and water is entering into this one and here. Gates are operating here and they are releasing water for left side and right side. So before releasing water, they have to take care of silt entering into the canal. Otherwise, there will be a silt, large amount of silt will collect on the canal and the purpose of the canal will not be solved. So silt excluders, silt ejector are also provided in this canal system. At the under spaces part also they have to provide this barrage. And here is also one divide wall is there, and this is the regulator portion. This is the diagram of this is a photo of this is the photo of a barrage. You see here, these are the spillway portion, and these are the undersluice portion. This is the barrage in our CWPRS. This is a model. Here you see all of your. This is the divide wall. दिख रहा है क्या? There is a difference. ये दिख रहा है क्या आपको ऐसा? नहीं दिख रहा है. इधर इधर थोड़ा बड़ा सा है. ये डिवाइड वाला है. These two are अंडर स्पीसीज है. इधर क्रेस्ट नीचे है. आपको दिख रहा है क्या? नहीं दिख रहा है. इधर क्रेस्ट नीचे है. ये जो क्रेस्ट है ना ऊपर है. देखो ब्लू कलर में. These are the spillways. ये जो है अंडर, ये जो है हेड रेगुलेटर है. आपको अभी बता, ये भी हेड रेगुलेटर. The water is flowing like this. These are the all are the spillways, and left side, right side, under spaces are there, and two head regulators are there. And these are the guide buds we have studied in CWPRS. And here also you can see in pink color, these are the guide buds in the downstream side. Here is the one bridge. I explained about the bridge. Only there are here one barrage is the downstream of bridge, proposed bridge. This is the proposed rail bridge. This is proposed road bridge. This is the overall barrage. This is the reverse plan. So in this case, what we have studied, the barrage is already existing, and this bridge also have given this bridge, railway bridge. And the alignment of yesterday also you have seen in the physical model. There are three bridge piers are there. They are aligned in same line. Like that, we have aligned these three piers in one line. What will happen if you do like this? The cover is happening due to the high discharge. It will be low. It should not affect the existing structures. Here, these are the guide bands proposed for this bridge, for three bridges including. This is the model of CWPRS. Here you see, this is the green one is Pokla barrage. This is road bridge, yellow one. White one is BMR. And these are the guide bands we have studied CWPRS in physical model of river Yamuna, and we have suggested to the project authority. DMRC है, वोकला के डाउनस्ट्रीम में. दिल्ली मेट्रो लाइन. Under sluices I explained you. Divide wall also I explained. The length of the divide wall should be 2/3 of the head regulator. इधर देखो, width of the head regulator. This length of the upstream length of the divide wall should be 2/3 of the regulator. So that the water pocket will be created here. So water will be maximum water we can draw from this head regulator, and still free water will be can get by this head regulator and barrage. River training works. I explained about the approach road. Will explain here. This is the approach road. So here you see the total width of the river is like this high. Suppose 1.5 kilometer, but waterway we have provided is only 175 meters. The rest of the thing we have closed. This will call approach embankment. We have to design this one model. Also, we have to design upstream and downstream guide bands and spurs. Also, I have discussed. Hmm. In this, you see, yeah. This is the total river width, and we have constructed a bridge here so that the river will be constricted. And these are the guide bands we have provided. This is the upstream. This is the upstream side, and this is the downstream side. If you visualize this one, this will be like this. This is the top of the guide band. After the sloping portion, after the transit diaphragm, we have given. Totally with then the available material which is available in the river, and after that we are giving protection to the guide bands. In spurs also, only we are constructing the local material and we have go for design of protection works to the spurs. Here you see the protection is after extracting the header parameters from the physical or mathematical model, we are conducting the we are designing the protection works in the sloping portion, and this is the toe wall and this is the launching out. So this will be support and protect the main structure. These are the protection works. I will explain next how we will design this protection works. Just you see what are the protection works and where we have to give the protection work. This is the then available material we have to construct this one. After that we have to provide the protection works. This protection works will be the crates gabion, loose boulders, CC blocks, geo bags. That is different materials. I will explain. I will discuss about the materials also. This is the design of protection of sloping bank. Here we are calculating the weight of crates. This is the generally now I am explaining about the only this protection works in gabion crates. In sloping portion, we are calculating the weight of stones by using this formula, waste batch formula. This is the velocity and this is the K value. By using this value and weight, we will get 781.27, and thickness of pitching of this particular protection works on the sloping we will get by this equation v square by 2g into ss minus 1, that will be 0.7. After that we are calculating the volume of crates, and after getting volume of crates we are we are deciding the size of the crates. Here you see, here in this portion, first we are calculated the this weight of this stone. After that, thickness of this one. This is the thickness. This is the thickness of weights. After that, this is the launching gap. This is the thickness of launching gap. This is the length of the launching. This is the toe wall. The use of toe wall is to support the slope protection. So like that, volume of this portion we have decided, and have designed this one, thickness and volume, and we have the design of sloping portion like this. Now we'll go for launching apron. Before going to design the launching apron portion, everyone should calculate the depth of cover. In two ways, we can calculate the depth of cover by using these two formulas. The higher one we are taking, which one is higher value, and after that we are multiplying by the quantity of stone in apron we are getting by this formula. This is root 5 because we have assumed that slope of the bank is 2 is 2, horizontal is to 1 1. While in Pythagoras equation we will go for slope under root of 2 square plus 1, that is 5. We are calculating the amount, the stone quantity. After that into depth of cover, and we are getting depth of cover from this equation, and the thickness of the slope pitching. Just now I explained about this by using this equation here, by v square by 2g. Here we will get the thickness of the pitching and the sloping bank. So by using all these parameters, we will get the quantity here, and length of the launching apron will decide actually in length of the launching apron should be 2.7 into depth of cover. Generally, this equation will be for normal straight portion, but in convex portion that will be 1.5 times the D max. So this will be, we have to take for the length of the, if we know the depth of cover, multiplying 1.5 will give the length of the launching apron. Here you see, this is the length of the launching apron. After knowing this thickness of apron, you should know by quantity of stone, by length of the apron, you will get the thickness of the apron. This is the thickness of the apron. So, sometimes it will be more than 1.52. Then we will go for 2 layers of crates in 2 layers. Here you see apron of stone in crates of size L in 2 layers, like that I have written. What is the meaning of this one? The boulders which we have designed should be safe and should not move while the maximum discharge is hitting the flow is hitting to the protection works. It should protect the that guide band or spur, anything, the hydraulic structure. Like that we are calculating, and also volume just now I explained about in sloping portion. Volume is also we are calculating in launching apron portion. This is the common for material is same. Spur also we are constructing with earthen embankment, like, but the orientation and length and the location is different. Guide band location is different. Spur location is different. Okay, so the protection works are same for spur, guide bands, embankments, same procedure. Sloping portion, launching apron, toe wall, all are same. Okay. These are the components of embankments, guide bands, spurs, permeable screens, bank revetment, geotubes, and bags. These are the protection materials we are using in, generally we are using in to protect the bank or rivers. Generally sandbags, boulders, geotextile bags, geotextile tubes, sand-filled geomattress, geomembrane, geogrids, RCC propellants, concrete blocks, GI wire mesh. These are the new comings, but in earlier days only timber and boulders are generally used since older time to protect the banks. Nowadays, all these geosynthetic material we are using for bank protection works. These are the RCC porcupines. The use of these protection works are also very much important. This type of screens and we are using in braided or the rivers which are carrying high silt like Brahmaputra. We are suggesting this type of protection works to stabilize the banks. So how these are working? Whenever you put like this, whenever flood comes with flow and they are carrying huge amount of silt, the velocity will be reduced here and the silt will be deposited due to these screens. And flood embankments are generally constructed along the banks to protect the areas nearby the banks. So these are also earthen embankments and protection works. I just now explained how to protect these embankments by using slope protection, launching apron and tow wall. And cross section of the embankment designed to obtain the minimum cover of 0.6 meter above the CPS gradient inside the body of the embankment. Everyone should know this one, otherwise it will be fail. The CPS gradient within the your embankment only. The minimum freeboard of 1.5 meter is provided to prevent the overtopping. And that is also I have explained 1.5 meter of freeboard. And these are the typical diagrams of the embankment. Here there is a road on the embankment. This is the sloping portion. Here you see silt deposition. Without embankments, there is a very less siltation was occurred in this channel. While coming to the uh, embankments on the both banks, left and right, siltation is very higher quantity siltation was done. Here you see embankments are on both sides. Here also you can find the siltation. Here you see different types of riverment on the banks for various rivers. This is the Swan River photos. So see here, this is the sloping portion and launching apron is here you can see or not. Here you see. This is the sloping portion. This is the launching apron. Okay, and these are the boulders in crates. Here you see this is the embankment, earthen embankment, and they have protected the slope by using these stone crates. This is the launching apron. After vegetation, you are not seeing the boulders there. So by growing these plants also, they are protecting this protection works. Here you see the river training works in guide bunds. Here you see the guide bunds on the upstream. This is the shank portion, and this is the downstream shank. This is curved portion on the downstream and this is the upstream portion. This will be decided by the modeler in the model studies only. These are the different types of guide bunds. These are the straight guide bunds and these are the elliptical guide bunds. Whenever the flow is oblique with some angle, then we will go for the elliptical guide bunds. This will be suggested only after the studies in mathematical model study work only. Guide bunds. See here different types of guide bunds we have constructed in different models in CWPRS. Here you see the very long guide bunds we have suggested in Yamuna model at on river Yamuna in near ITO bridge. So how flow is approaching this river. You can visualize here. Here also there are number of guide bunds we have constructed in river Yamuna, and there are 22 bridges, 3 barrages we have studied on this river Yamuna from Palla to Jaipur. We have a physical model in CWPRS and the total reach is 50 kilometers, but only in 25 kilometers there are 22 bridges are there. So you can see here there are continuous bridges you can find out. These are the pink color are the guide bunds we have suggested, and flow is only flowing through these bridges. you can find out this channelization of flow. You can find out this velocity is only in this direction. If you don't know if water is there but stagnant water is there in this left side, but there is no flow here, only flow you can see in this channel only. So here also you can see this floats we have taken to know the velocity of the flow of the river. So flow is approaching from one river to other river in this path only. So guide bunds are working properly in this Yamuna river. So flow is always safely passing through from one bridge to the other bridge. This is the bridge, Kosi river. There are many bridges are there in this also. So we have uh, studied many guide bunds on this river. Large long guide bunds also we have studied here. You can see by these photographs. Spurs. Spurs are the training measures used for deflecting, attracting the flow towards the bank. So the purpose of the spur also you should know before the design of the spur. Three types of spurs are there. First one is deflecting, attracting, normal. The purposes are very different. Suppose flow is coming like this. If you want to divert flow from this one, a normal spur is to divert the water from water should not come to the bank. This is the normal spur, and the other one is attracting spur. The other one is this is attracting spur. So the direction of flow is should be flow direction. Means water will come like this and it will be come to the bank. So if you want to divert water to the bank, suppose a holy place is there, some temples are there, some ghats we have constructed here. Water is not coming this way. So by constructing this attracting spur, water will be attracted by this spur and it will be the purpose of the spur will be served and water will come here. The use of this spur will be they will use water. The other one is repelling spur. The opposite direction of flow. This is the repelling spur. This is also to divert the water in the other direction. So the length of the spur should not be 20% of the total length. Suppose this is the L, it should be 20% of the L. It should not encroach the waterway of the tube. And the spacing sometimes the series of spurs also we are using in some rivers. Series of spurs also we are using to divert the water from the banks. In this case, the spacing should be 2 to 3 times of the length of the spur. Here you can see the normal spur and this repelling spur and types of this attracting spur. Just now I explained all these three types of spur. And the construction should not be maximum 30%. Spacing is 4.25 times the length. No, this is very important. In this one, here you see this is the bank. This is the river bank. and this is the spur. This is spur. This is called shank, and this is the launching apron portion. So the height of this spur would be decided by the maximum HFL plus 1.5 freeboard. This is generally, I will write freeboard. It will be differ from 1 to 2 meter like that depending upon the discharge. And this is the launching apron. The length of the launching apron in this case is covered depth into D max. In this nose portion, I have to go for 2 times of D max. And in the shank portion, we'll go for 1.5 times of D max. These are the designs of spurs. And here you see this crates, stone crates actually at the embankment they have constructed. After that slope pitching they have done by using this slope protection just now explained. And this is the launching apron they have given. This is called nose. This is nose. The starting portion is nose. This one. And the back one is shank. Like this. It will be like this. This is the nose portion. This is shank portion. Here you see these are the model pictures. This is the shank, this is the nose, and this is the launching apron. And these are the series of spur we have studied in model. These are the RCC porcupines in photo. You see this is the bank. This is the sloping portion. And here we have there is a launching apron is also there. Due to siltation you are not visualizing here. These are the screens we have given in series as a spurs to protect this bank with to deposit the silt and to protect and strengthen this bank along this bank. And this is the bamboo porcupines. Generally bamboo porcupines are used in Brahmaputra river also. So they have constructed here bamboo spur into the river. Here design, just now explained, this is the bank and this is the spur. This is called shank and this is the nose and this is the launching apron. And this is the launching apron of the embankment. Sufficient freeboard also have HFL plus sufficient freeboard. Nose and shank portion. 2D max just now explained everything. And these are the photographs of river Yamuna. This 50-kilometer reach. There are series of spurs we have given in Yamuna river. You see, actually what happened here, the Vajrabad barrage is constructed here, the first structure in Yamuna river. The water is hitting here, you can see this is the left bank, this is the right bank. So water is flowing through the right bank. After that it is going to the left bank. Again it is coming to the right bank. Again it is going to the right bank and again it is like this. But Indraprastha barrage is there here. So water is diverted from here. So we have to divert the water towards Indraprastha barrage. So we have given the series of spur in this location so that water is here diverted towards Indraprastha barrage. Okay, these are the guide bunds. Pink color are guide bund and yellow color are spurs. Here you can see in Proto also, this in Google image, the series of spurs in river Yamuna also you have visualized here. These are the series of spur we have given in physical model at OC. These are the spurs in actual Proto. These are the model. These are the permeable screen. The design of permeable screen will be like this. The height is 3 meters and you have to tie here, and it will be in cone shape 3. Okay, and some material should be you have to keep kept in between in this portion, so that some janky type local um, trees, small trees you have to remove and you have to put inside this, so that it will be better and the large amount of silt will be deposited here. These are the performance of porcupines you can visualize here. These are the photographs I have taken during my site visits. This is the Brahmaputra river protection works. Here you see the bamboo permeable screens used as a protection works, bank protection works. This is the design of a bamboo. Nowadays bamboo protections are not using, all are using this RCC porcupines only. Bank revetment just now I have shown here. This is the bank pitching. So slope protection they have given. This is the launching apron. This is called bank pitching also. These are the geobags. Filling the local material sand in the geobags or geotubes. This type of protection works are also doing by project authorities in some states where there is a shortage of rocks, boulders. They are going this type of protection works to protect their banks. This is geocells. These are the geobags used for the sloping portion, launching apron also. Cement bags also, the earlier cement bags only we are using. Nowadays geobags we are using. CC blocks also in Gandak River. A large amount of CC blocks for used for launching apron and the sloping portion in Gandak River. These are the geotubes used as a bank protection works in UP. This is Sharda River and sand cement bag revetment. This is very old type of revetment, and using this bamboos or wooden logs and tires, the car or two-wheeler tires, putting inside. And this is also one type of protection works. Earlier days people are doing like this. Wooden logs also, and this is the vertical gabion. This type of protection works we are doing, we are giving, we are suggesting for the Bass River. Yesterday, Madam Chonchkad, Himachal rivers, the velocities are very high, steep slopes. They are we are observing in this type of rivers. So the due to the high velocities, this type of protection works we are suggesting for this one. This is the vertical gabion wall in 3 meters. So depth of the rivers in boundary, yesterday in my first lecture I explained the depth of the river is very less, but velocities are very high. The slopes are also very high. In this case, we are giving this type of protection works. This is the gabion stone crates, and this is the launching apron again. Two layers of launching apron we have suggested, and this is the toe wall. You can see here damaged this gabion wall. Some of the photographs of sites you can visualize here. These are the dressing of banks before the before done before doing the construction of protection works. This is also dressing of slopes. You can see here sloping bank they are providing boulder pitching as a protection works. Here you see the launching apron, laying of launching apron. Here you can see this sloping portion they have uh, given this riprap with boulders. Here you see they have given this boulder as a loose boulder as slope protection. Below that granular filter. What we are doing is suppose this is the original soil. So before that placing the geosynthetic material production works, have to fill the sand 30 centimeter sand. After that place a geosynthetic material. After that again 30 centimeter sand. Now geosynthetic material should be sandwiched between sand layers 30 centimeter, 30 centimeter, so that it will water, the excess water which is on the upstream will be drained through this filter. Nowadays filters we are using. Earlier days they are using granular filters. So geosynthetic filter will be provided along total launching up. This is a very important thing. Nowadays we are using geosynthetic filter. Earlier they are using granular filter like this type of granulars. Toe wall protection, you can see here, this is the toe wall protection. Rock feldspar with embayment. Stepped stone spur. This is Gabion stones only. This is also damaged spur. This is also damaged spur. Series of spurs. These are also series of spur given in some hilly rivers, bamboo porcupines. These are the model studies diagrams. Here you see how studies of spur, how it normal spur, how it is diverting water from its bank, and scour will take in place near the nose of the launching apron. You see here, and apron also disturbed here with apron. Model studies also scour hole, you can see here how much cover is has occurred near the nose. Thank you. One thing I forgot. In physical model, what will happen when discharge is coming from upstream, so that water is going to this, some water is coming like this also. So care should be taken. The worst environment which is coming from here, it should not hit and it should not damage to the your environment. So it should be like this. And it will go like this. If it will be in this zone, your approach environment, it will be damaged and water will flow like this. So this will be shown in mathematical physical model. The worst environment should be taken care in physical model. Any doubts? Tomorrow we will take the hands-on on how we place bridges and embankments also, levees. Okay, thank you.
हाँ पीडीएफ डाल दीजिए ठीक है आप हाँ वो तो हम यहाँ पे सेव भी कर रहे हैं फिर इसमें भी डाल देंगे
अभी हम लोग मैडम